हेलो दोस्तों, बिजनेस माइंड में आपका स्वागत है। और अभी हम कर रहे हैं इकोनॉमी। ठीक है। इससे पहले चैप्टर 2 कंप्लीट कर चुके हैं। अब स्टार्ट करेंगे प्रोडक्शन एंड कॉस्ट। इन द प्रीवियस चैप्टर वी हैव डिस्कस्ड द बिहेवियर ऑफ द कंज्यूमर। इन दिस चैप्टर एज वेल एज इन द नेक्स्ट वी शैल एग्जामिन द बिहेवियर ऑफ अ प्रोड्यूसर। पहले में क्या करा था? कस्टम कंज्यूमर जो होता है, कंज्यूमर का बिहेवियर कैसा होता है। अब क्या करेंगे? प्रोड्यूसर जो होता है, जो प्रोड्यूस करता है चीज़ों को, उसका बिहेवियर। प्रोडक्शन इज द प्रोसेस बाय विच इनपुट्स आर ट्रांसफॉर्म इनटू आउटपुट। प्रोडक्शन इज कैरिड आउट by producers or firms. A firm acquires different inputs like labor, machines, land, raw materials, etc. It uses these inputs to produce output. This output can be consumed by consumers or used by other firms for further production. For example, a tailor uses a sewing machine, cloth, thread, and his own labor to produce shirts. A farmer uses his land, labor, a tractor, seed, fertilizer, water, etc. to produce wheat. A car manufacturer use land for a factory, machinery, labor, and various other inputs, steel, aluminium, rubber, etc. to produce cars. A rickshaw puller uses a rickshaw and his own labor to produce rickshaw rides. A domestic helper uses her labor to produce cleaning services. We make certain simplifying assumption to start with. Production is instantaneous. In our very simple model of production, no time elapses between the combination of the inputs and the production of the output. We also tend to use the terms production and supply synonymously and often interchangeably. In order to acquire inputs, a firm has to pay for them. This is called the cost of production. Once output has been produced, the firm sells it in the market and earns revenue. The difference between the revenue and cost is called the firm's profit. We assume that the objective of a firm is to earn the maximum profit that it can. In this chapter, we discuss the relationship between inputs and output. Then we look at the cost structure of the firm. We do this to be able to identify the output at which firm's profits are maximum. Production functions. The production function of a firm is relationship between inputs used and output produced by the firm. For various quantities of inputs used, it gives the maximum quantity of output that can be produced. Consider the farmer we mentioned above. For simplicity, we assume that the farmer uses only two inputs to produce wheat: land and labor. A production function tells us the maximum amount of wheat he can produce for a given amount of land that he uses, and a given number of hours of labor that he performs. Suppose that he uses 2 hours of labor per day and 1 hectare of land to produce a maximum of 2 tons of wheat. Then a function that describes this relation is called a production function. One possible example of the form this could take is Q equals to K into L, where Q is amount of wheat produced, K is the area of land in hectares, L is the number of hours of work done in a day. Describing a production function in this manner tells us the exact relation between inputs and output. If either K or L increase, Q will also increase. For any L and K, any any L and any K, there will be only one Q. Since by definition we are taking the maximum output for any level of output inputs, a production function deals only with the efficient use of inputs. Efficiency implies that it is not possible to get any more output from the same level of inputs. A production function is defined for a given technology. It is the technological knowledge that defines the maximum levels of output that can be produced using different combinations of inputs. If the technology improves, the maximum levels of output obtainable for different input combinations increase. We then have a new production function. The inputs that a firm uses in the production process are called factors of production. In order to produce output, a firm may require any number of different inputs. However, for the time being, here we consider a firm that produce output using only two factors of production, labor and capital. Our production function therefore tells us the maximum quantity of output Q that can be produced by using different combinations of these two factors of productions, labor and capital K. We may write the production function as Q equals to F LK, where L is labor, K is capital, Q is the maximum output that can be produced. Production function factor labor capital 0 1 2 3 4 5 6, labor 0 0 0 0 1 0 1 सेक 1 का 1 2 का 3 ऐसे करके ये टेबल पूरी फॉर्म बनेगी. A numerical example of production function is given in table 3.1. The left column shows the amount of labor and the top row shows the amount of capital. As we move to right along any row, capital increase, and we move down along any column, labor increase. अगर डाउन जाएंगे तो फिर क्या होगा, लेबर इंक्रीज हो रही है, और इधर जाएंगे तो फिर अमाउंट इंक्रीज हो रहा है फॉर डिफरेंट वैल्यूज ऑफ द टू फैक्टर्स. इसको बाद में देखेंगे. Two factors of the table shows the corresponding output levels. For example, with 1 unit of labor and 1 unit of capital, the firm can produce at most 1 unit of output. With 2 units of labor and 2 units of capital, it can produce at most 10 units of output. With 3 units of labor and 2 units of capital, it can produce at most 18 units of output, and so on. In our example, both the inputs are necessary for the production. If any of the inputs become zero, there will no production. With both inputs positive, output will be positive. As we increase the amount of any input, output increases. Isoquant. In chapter 2, we have learned about indifference curves. Here we introduce a similar concept known as isoquant. It is just an alternative way of representing the production function. Consider a production function with two inputs, labor and capital. An isoquant is the set of all possible combinations of the two inputs that yield the same maximum possible level of output. Each isoquant represents a particular level of output and is labeled with that amount of output. Let us return to table 3.1. Notice that the output of 10 units can be produced in three ways: 4L 1K, 2L 2K, 1L 4K. All these combination of L, K lie on the same isoquant, which represents the level of output 10. Can you identify the sets of inputs that will lie on the isoquant Q is equal to 50? The diagram here generalizes these concepts. We place L on the x-axis and K on the y-axis. We have three isoquants for the three output levels, namely Q equals to Q1, Q equals to Q2, and Q equals to Q3. Two input combinations L1 K2 and L2 K1 give us the same level of output Q1. If we fix capital at K1 and increase labor to L3, output increase and we reach a higher isoquant Q equals to Q2. When marginal products are positive with greater amount of one input, the same level of output can be produced only using lesser amount of the other. Therefore, isoquants are negatively sloped. इस तरीके से नेगेटिव स्लोप हो जाएंगे. The short run and the long run. Before we begin with any further analysis, it is important to discuss two concepts: the short run and the long run. In the short run, at least one of the factor, labor or capital, cannot be varied and therefore remains fixed. In order to vary the output level, the firm can vary only the other factor. The factor that remains fixed is called the fixed factor, whereas the other factor which the firm can vary is called the variable factor. Consider the example represented through table 3.1. Suppose in the short run capital remains fixed at 4 units, then the corresponding column shows the different levels of output that the firm may produce using different quantities of labor in the short run. In the long run, all factors of production can be varied. A firm, in order to produce different levels of output in the long run, may vary both the inputs simultaneously. So, in the long run, there is no fixed factor. Long run में क्या होता है, कोई भी फिक्स फैक्टर नहीं होता. ठीक है. फॉर एनी पर्टिकुलर प्रोडक्शन प्रोसेस, लॉन्ग रन जनरली refers to a longer time period than the shorter run. For different production processes, the long run periods may be different. It is not advisable to define short run and long run in terms to say days, month and years, or we define a period as long run or short run simply by looking at whether all the inputs can be varied or not. Total product, average product and marginal product. Total product, suppose we vary a single input and keep all other inputs constant, then for different levels of that input we get different levels of output. This relationship between the variable input and output, keeping all other inputs constant, is often referred to as total product TP of the variable input. Let us again look at 3.1. Suppose capital is fixed at 4 units. Now in the table 3.1 we look at the column where capital takes the value 4. As we move down along the column, we get the output values for different values of labor. This is the total product of labor schedule with K2 equals to 4. This is also sometimes called total return to or total physical product of the variable input. This is shown again in the second column of table in 3.2. Once we have defined total product, it will be useful to define the concepts of average product AP and marginal product MP. They are useful in order to describe the contribution of the variable input to the production process. Average product is defined as the output per unit of variable input. We calculate it as ALP, TLP. The last column of table 3.2 gives us a numerical example of average product of labor with capital fixed at 4 for the production function described in table 3.1. Values in this column are obtained by dividing TP column 2 by L column 1. Marginal product. Marginal product of an input is defined as the change in output per unit of change in the input when all other inputs are held constant. When capital is held constant, the marginal product of labor is marginal product, change in output, change in input, delta TPL or delta L, where delta represents the change of the variable. The third column of table 3.2 gives us a numerical example of marginal product of labor with capital fixed at 4 for the production function described in table 3.1. Values in this column are obtained by dividing change in TP by change in L. For example, when L changes from 1 to 2, TP changes from 10 to 24. MP TP at L units minus TP at L minus 1 units. Here change in TP equals to 24 minus 10 equals to 14. Change in L equals to 1. Marginal product of the second unit of labor, 14 divided by 1 equals to 14. Since inputs cannot take negative values, marginal product is undefined at zero level of input employment for any level of an input. The sum of marginal products of every preceding unit of that input gives the total product. So total product is the sum of marginal products. Total product, marginal product and average product. Labor, total product, marginal product और average product. 0 0 0 कुछ भी नहीं है. 1 10 10 10 2 24 14 और 12 ऐसे पूरी टेबल फॉर्म हो जाएगी. Average product of an input in any level of employment is the average of all marginal products up to that level. Average and marginal products are often referred to as average and marginal returns respectively to the variable input. The law of diminishing marginal product and the law of variable proportion. If we plot the data in table 3.2 on graph paper, placing labor on the x-axis and output on the y-axis, we get the curves shown in the diagram below. Let us examine what is happening to TP. Notice that TP increases as labor input increases, but the rate at which it increases is not constant. An increase in labor from 1 to 2 increase TP by 10 units. An increase in labor from 2 to 3 increases TP by 12. The rate at which TP increases, as explained above, is shown by the MP. Notice that the MP first increases up to 3 units of labor and then begin to fall. This tendency of the MP to the first increase and then fall is called the law of variable proportion or law of diminishing marginal product. Law of variable proportion says that the marginal product of a factor input initially rises with its employment level, but after reaching a certain level of employment, it starts falling. Why does this happen? In order to understand this, we first define the concept of factor proportion. Factor proportion represent the ratio in which the two inputs are combined to produce output. As we hold one factor fixed and keep increasing the other, the factor proportions change. Initially, as we increase the amount of the variable input, the factor proportion become more and more suitable for the production and marginal product increases. But after a certain level of employment, the production process becomes too crowded with the variable input. Suppose table 3.2 describes the output of a farmer who has 4 hectares of land and can choose how much labor he wants to use. If he uses only one worker, he has too much land for the worker to cultivate alone. As he increases the number of workers, the amount of labor per unit land increases, and each worker adds proportionally more and more to the total output. Marginal product increases in this phase. When the fourth worker is hired, the land begins to get crowded. Each worker now has insufficient land to work in efficiently. So the output added by each additional worker is now proportionally less. The marginal product begins to fall. We can use these observations to describe the general shapes of the TP, MP, and AP curves as below. Shapes of total product, marginal product, and average product curves. An increase in the amount of one of the inputs, keeping all other inputs constant, results in an increase in output. Table 3.2 shows how the total product changes as the amount of labor increases. The total product curve in the input-output plane is a positively sloped curve. Figure 3.1 shows the shape of the total product curve for a typical firm. We measure units of labor along the horizontal axis and output along the vertical axis. With L units of labor, the firm can at most produce Q1 units of output. According to the law of variable proportion, the marginal product of an input initially rises and after a certain level of employment, it starts falling. The MP curve therefore looks like an inverse U-shaped curve as in figure 3.2. Let us now see what the AP curve look like for the first unit of the variable input. One can easily check that the MP and the AP are same. Now, as we increase the amount of input, the MP rises. AP begins the average of marginal products also rises, but rises less than MP. Then, after a point, the MP starts falling. However, as long as the value of MP remains higher than the value of the AP continues to rise. Once MP has fallen sufficiently, its value becomes less than the AP and the AP also starts falling. So AP curve is also inverse U-shaped, like this, U-shaped. ये जैसे हो रहा है U-shaped. As long as AP increases, it must be case that MP is greater than AP. Otherwise, AP cannot rise similarly when AP falls. MP has to be less than AP. It follows that MP curve cuts AP from above at its maximum. Figure 3.2 shows the shapes of AP and MP curve for a typical firm. The AP of factor 1 is maximum at L. To the left of L, AP is rising and MP is greater than AP. To the right of L, AP is falling and MP is less than AP. Returns to scale. The law of variable proportions arise because factor proportions change as long as one factor is held constant and the other is increased. What if both factors can change? Remember that this can happen only in the long run. One special case is the long run occurs when both factors are increased by the same proportion or factors are scaled up. When a proportional increase in all inputs results in an increase in output by the same proportion, the production function is said to display constant returns to scale (CRS). When a proportional increase in all inputs results in an increase in output by a larger proportion, the production function is said to display increasing returns to scale (IRS). Decreasing returns to scale (DRS) holds when a proportional increase in all inputs results in an increase in output by a smaller proportion. For example, suppose in a production process, all inputs get doubled as a result. If the output gets doubled, the production function exhibits CRS. If output is less than doubled, then DRS holds, and if it is more than doubled, then IRS hold. Returns to scale. Consider a production function Q equals to f x1 x2 where the firm produce q amount of output using x1 amount of factor 1 and x2 amount of factor 2. Now suppose the firms decide to increase the employment level of both the factors t greater than 1 times. Mathematically we can say that the production function exhibits constant returns to scale if we have f tx1 tx2 equals to 2t into f x1 x2. That is the new output level t x1 x2 is exactly t times the previous output level t x1 and x2. Similarly, the production function exhibits increasing returns to scale if f t x1 x2 is greater than t f x1 x2. It exhibits decreasing returns to scale if t x1 x t x2 is smaller than t f x1 x2. Cost. In order to produce output, the firms needs to employ inputs, but a given level of output typically can be produced in many ways. There can be more than one input combinations with which a firm can produce a desired level of output. In table 3.1, we can see that 50 units of output can be produced by three different input combinations: L equals to 6, K equals to 3, L equals to 4, K equals to 4, and L equals to 3, K equals to 6. The question is which input combination will firm choose. With the input prices given, it will choose that combination of inputs which is least expensive. So for every level of output, the firm chooses the least cost input combination. Thus the cost function describes the least cost of producing each level of output, giving prices of factors of production and technology. Cobb Douglas production F production function. Consider a production function q equals to x1 alpha x2 beta where x alpha and beta are constants. The firm produce q amount of output using x1 amount of factor 1, x2 amount of factor 2. This is called a Cobb-Douglas prediction function. Suppose with x1 is equal to x1 and x2 is equal to x2, we have q0 units of output, that is q0 x1 alpha x2 beta. If we increase both the inputs t t is greater than t1 times, we get the new input q1 tx1 alpha tx2 beta t alpha plus beta x1 alpha x2 beta. When alpha and beta equals to 1, we have q1 equals to 2 q0, that is the output increase t times, so the prediction function exhibits CRS. Similarly, when alpha beta is greater than 1, the prediction function exhibits IRS. When alpha beta is smaller than 1, the prediction function exhibits DRS. शॉर्ट रन कॉस्ट ये पढ़ेंगे अब कल.